right? We're not talking about force because we can get rid of the m, the mass, and that's the whole thing that allows us to talk about gravity as the same as inertia and being a worldline curvature field, is because we got rid of the mass out of the equation. It doesn't depend on the mass. So we always talk about the acceleration, gm over r squared, not the force, gmm over r squared. If you're in this, whatever it is that's falling towards the Earth, you're standing in there, right? I'm holding this. I don't feel any pressure against the floor. If I let go, what will happen? Nothing happens. It stays suspended in midair as we're falling, because we're all accelerating with the same thing. From the outside, you're looking, you see everything's falling down, right? Inside, it looks very strange. You say, you let go, nothing's falling. And similarly, I don't feel any pressure of the floor against me. I'm not falling either, not only the glass. But we're all, of course, looking from the outside, we're all falling down with the same acceleration. So why, of course this is not pressing against my palm. If I move my palm, it just stays there. And my feet are not pressing against the floor. Okay? The satellites are in free fall towards the Earth. Okay, you all, circular orbit, exactly what I said before. You have tangential velocity, right? The Earth acceleration pushing you in this way, changing the direction of your speed, right? But you're falling into the Earth at any instant. Right? You're in free fall. You're constantly falling into the Earth. Just as you fall, you're also going to the side. You fall in, you go to the side, you fall in, you go to the side, and you end up making a circle. There's nothing holding you up, so to speak. You're not fighting against gravity. You're falling in, just you also have this tangential velocity, and the magnitude of that velocity remains constant. And therefore you, let's say, have a circular orbit. Okay? Now, when we observe it within this little elevator, so to speak, this little box that's freely falling, so all these measurements are made simply in this little box. We have no way of knowing that this box is actually falling towards a matter source, a curvature of space-time source, right, gravity source, unless we would look outside. Now, what would it mean to say that we don't know? I mean, of course we know, right? I mean, somebody constructed this little laboratory and made it fall down. Obviously, they know that there's a planet there and it's falling towards a planet. So what might it mean to say that we don't know that this is actually falling, so as far as we're concerned, these particles are in inertial motion, and so on and so forth?
That going back to what gravity is the same as acceleration, essentially.
Right, but correct. But what is that? Somebody can say yes, but you know that it's not. I mean, one is gravity and one is acceleration. So what does it mean to say that they're the same? They're not the same.
They're equivalent.
Okay, they're equivalent, and therefore, but they're not the same. You can always just look outside and see if there's a mass there. I mean, if you see the mass, you see you're accelerating towards it.
Well, you could just accelerate faster, and you could assume there would be a bigger mass. You could say you could have a...
Yeah, but you could look outside and see if there is, in fact, a bigger mass. I mean,
Well,
if you know what your acceleration is,
right.
How did you know that? What did you measure it relative to?
The mass.
So then you know there's a mass.
But you could say you could put a rocket on the back of your,
Well, you just look to see if there's a rocket.
You couldn't see the rocket.
What?
You couldn't see the rocket.
Well, you take a spacewalk outside the ship, and it's physics to do an experiment. Why are we fooling ourselves? So the answer is that since there's no way to measure the difference here within this box, we want to, in physics, talk only about local measurements. We want to be able to talk about things without needing to go outside. And if we find that there are things which are totally equivalent locally, that tells us something about nature. Okay, that tells us that it's not a trivial thing to say that the only way you can tell that this is really gravity, so to speak, is if you look outside. It's an amazing thing that there's no way to tell the difference. It's a consequence of this amazing counterintuitive idea that two things of very different masses will fall with the same speed and acceleration. Right? That's a very deep property. It tells us something. So it's not that we don't know or have no way of knowing whether this is gravity or acceleration. Obviously we do. The point is that we have no way of knowing if we remain within our little local realm. And that tells us something deep. Okay, because in physics, if you can't measure the difference between two things, there's no meaning to say that they are different. Clearly they are different, but only when you go non-locally. Locally, they're the same thing. That's the point. Okay, so if we're restricting our statement to local things, they're the same. It's the same thing. It's not, well, this is this, and they look like the same. It's the same thing. Okay.